Okay. Hello, my name is Hongjun Gang in Gwangju Institute of Science and Technology. I'm here to present the paper titled Flip-Pelt, Motor-Driven Peltier Element for Rapid Summer Stimulation and Congruent Pressure Feedback in Virtual Reality. First, please take a look at these images. There's a cup filled with Coke and bowl filled with soup. Imagine holding or picking up each cup and bowl. What sensation do you feel? You might imagine the pressure, the cold or hot sensations, the weight, and your skin being stretched. Now, imagine you pick up the Coke but don't feel the cold, or pick up the bowl but don't feel the heat. I would feel like something is wrong. Similarly, in certain situation or object, temperature is as important as other tactile sensation in helping us perceive and understand the world around us. However, providing such thermal feedback in virtual environment presents certain challenges. One of the key challenges is providing thermal feedback when hot or cold objects contact the skin. Simulating contact with objects of the specific temperature requires a high level of temporal congruency between pressure and thermal feedback. This means that the sensation of temperature must be felt immediately upon contact with the object. So one method to provide thermal feedback is by using a Peltier element. A Peltier element controls surface temperature by changing the current direction. However, it takes several seconds to reach the desired temperature. Then fluid-based methods have also been explored, but they also take time for the fluid to move from the chamber to the target area. So due to the inherently slow thermal response speed, it is difficult to synchronize with timing of contact. So we aim to address the delay in thermal response through a straightforward approach, just by directly flipping the Peltier element. The Peltier element has one side cooled and the other side warmed. And by using a motor to physically flip the element, we can convert the thermal response speed to the speed of the motor's response. Flip-Pelt is designed to use 8 motor-driven Peltier elements attached to the forearm. Each Peltier element can work individually and quickly, as shown in this video. In particular, the heat is transferred in the same way as contact with the actual heat source. So it ensures the temporal congruency between the pressure and thermal feedback. So later in front of the poster, you can see the simple version of Flip-Pelt operates. So I'll be happy to discuss it further with you. Okay, the first research question is, can Flip-Pelt users distinguish the stimuli patterns and stiffness levels of the forearm? The Flip-Pelt device designed with 8 elements, so allows for various combinations. In this design, we need to evaluate whether Flip-Pelt users can perceive different stimuli patterns and thus simulate the various virtual objects. Additionally, the motor-driven design of Flip-Pelt has the potential to simulate the stiffness by controlling the penetration depths. To demonstrate this potential, we will evaluate users can distinguish between different stiffness levels. So this evaluation will be conducted in Study 1. In Study 1, the experiment was conducted to distinguish between 5 stimuli patterns and 2 levels of stiffness. So in this study, the penetration depth of the Peltier element was personalized for each user. And then participants were tested by stamping an unknown pattern and stiffness on the forearm. And they had to identify which patterns and stiffness. These stimuli were given as either hot or cold. And then this study has 2 independent variables. IV1 is the thermal stimulation method comparing the without flipping Peltier method, which controls the Peltier element through current direction, with the with flipping Peltier method. IV2 is the presence of pressure, comparing the without pressure with pressure condition. So we compare across 4 conditions. So cold non-fresh refers without flipping Peltier and without pressure, and flip non-fresh refers with flipping Peltier and without pressure, and curve fresh refers without flipping Peltier and with pressure, and finally flip fresh or Flip-Pelt refers with flipping Peltier with pressure. So through these 4 conditions, we can evaluate the effects of each independent variable. As a result, the pattern recognition accuracy for the 5 patterns were highest in the Flip-Pelt and the lowest in a cold non-fresh. So when looking at each independent variable, the flipping Peltier method increased pattern recognition accuracy by 15%, and the with pressure method increased pattern recognition by 20%. So this indicates that both flipping Peltier and the pressure feedback contribute to improving pattern recognition of various objects. And the recognition accuracy of stiffness levels was only significant based on the presence of pressure. So in condition with pressure, participants were able to distinguish between sponge and metal with the accuracy of 80% and 89%. So this result demonstrates that Flip-Pelt not only provide various stimuli patterns, but also has an ability to simulate materials with different stiffness levels. So the second research question is, does the Flip-Pelt enhance the haptic experience in VR demo scenario through its rapid summer stimulation and congruent pressure feedback? So the Flip-Pelt can flip the Peltier in 450 milliseconds to provide rapid summer feedback. Additionally, this summer and pressure feedback are temporally congruent. Despite this technical advantage, we need to evaluate whether they actually enhance the haptic experience for users in VR scenarios. So this evaluation will be conducted in study 2. In study 2, we create 2 VR scenarios. The first demo, sensory massage, is the scenario where the user receives the massage with the hot or cold hand. And there are 3 massage types based on study 1 stimuli patterns. The degree to which the massage hand penetrates the forearm was calculated in unity, and pressure was applied according to match the corresponding depths. The second demo, take a shower, simulate the taking a shower with hot or cold water. So there are also 3 types of water streams, and the pressure varied based on the strength of the water flow. So the independent variable are the same as in study 1, and the dependent variable was evaluated using a HX model questionnaires to assess the haptic experience. As a result, in a sensory massage, the flipping Peltier showed a significantly higher HX score compared to the without flipping, and with pressure method also had a significantly higher HX score. And then flipping Peltier had a small effect size, while pressure had a large effect size. So this suggests that both the flipping Peltier and pressure feedback contribute to improving the haptic experience, but pressure plays a more crucial role in a sensory massage scenario. In a take a shower scenario, the flipping Peltier also showed a higher HX score, and then with pressure method had higher HX score. But the flipping Peltier had a large effect size, while pressure had a medium effect size. So this suggests that the flipping Peltier plays a more crucial role in improving the haptic experience in a take a shower scenario. So we gain several additional insights from study 2. The dominant haptic sensation varied depending on the scenario context. According to the open-ended question, 71% of participants identified pressure as the primary expected sensation in a sensory massage, while 64% identified thermal sensation as the primary expected sensation in a take a shower. So this suggests that in situations like take a shower, where thermal sensation is expected to be the main focus, it is important to replicate thermal feedback than pressure feedback. So therefore, this emphasizes the importance of replicating the thermal sensation of contact using rapid thermal feedback, such as that provide by Flip-Pelt. So furthermore, we can ask this question. So is Flip-Pelt only applicable to the forearm? We can also apply Flip-Pelt to areas such as the sole of the feet, and Flip-Pelt can be built into the sole of VR shoes, allowing users to feel the heat of lava ground or the cold of cave ground. So the motor quickly rotates to apply pressure and thermal stimuli to the skin with each step. So we can also apply a Flip-Pelt mechanism in a VR controller. The cylindrical Peltier element rotates inside the VR controller, allowing users to experience the holding a hot pan or holding a cold snowball. So we are able to draw a conclusion from this study. First, RQ1 was confirmed with Flip-Pelt distinguished 5 stimuli patterns with 83% accuracy and 2 stiffness level with 89%. Second, RQ2 was also confirmed, showing that the Flip-Pelt flipping Peltier method and pressure feedback significantly enhance the user haptic experience in VR demos. And lastly, there's some additional insight. In situations where the thermal sensation is the main expectation, rapid thermal feedback can enhance the haptic experience more than other sensations. So with this, I would like to conclude the presentation by emphasizing the importance of rapid thermal feedback during contact. Yeah. Thank you for listening to my presentation. Feel free to ask any question. I will do my best to answer. Thank you.
Any question?
This is Ning from the University of Maryland. Thank you very much for a great talk. I have a question about the way you generate the hot and heat temperature using the Peltier. Seems like there's no additional setup for driving away the residual heat from the Peltier area. Have you ever met any issue when you keep powering up the Peltier and both sides in the end all turning to the heat?
Yeah, okay. So I will show some slide in here. You know that for standard Peltier elements, if there is no heat sink, the cold side become warm along with the hot side. However, Flip-Pelt uses the both sides, so it can use a heat sink. To solve this, we use the multi-layer structures, maintaining the cold side need more current, and which makes the hot side even hotter. So this aluminum layer helps absorb some of the heat, and the silicone layer protect the skin from the hot side. So actually, it uses more energy to contain the dual side hot and cold, but it can keep the cold side cool for a longer time. So as you can see in this graph, the multi-layer structure helps keep the cold side colder for a longer time. But actually, this is the limitation. The 196 seconds is a little bit short time, but I think. But the point is, the standard Peltier element was 20 seconds to contain each side, both sides, hot and cold. So.
I see. Thank you.
Thank you.
Hi, this is Yu from Saarland University. It's a very cool work, and I just have a question about, so it's a flipping mechanism that hot and warm is a binary, and in the cylinder that you show, that's embedded in the VR controller, I wonder if the user touch in the middle point between the warm and cold, is it possible to feel something in between warm and cold? Would it make it warm? Is it possible to make it continuous by playing around the area of cold and warm that user touches?
So you mean, is it possible to stimulate the both warm and cold?
Some temperature in between.
So between, yeah. Yes, it's also the limitation. The cool side of dual side Peltier element fluctuate between the 16 Celsius and and 28 Celsius, so making it difficult to maintain the specific target temperature. So
yeah, but I just wonder if you tried, like with the cylinder example that you showed in the VR controller, like you have a cylinder that like rotates instead of flip in the VR controller, and I wonder if you try touching in the middle, would it feel like two different temperatures, or would it feel like being one just warmer, like it's warmer than cold, but cooler than hot temperature?
Okay, so you mean like this? There's some gap in the two sides.
Oh no, it's not with the flipping. It's one of the applications that you showed that's embedded in the VR controller.
Sorry. Actually, there's a time limit, so if you can.
Yeah, sure. Well,
Yeah, we can discuss later. And I know also we have more questions, and feel free to come to the poster at the end of the room.